Okay, pre-calculus students, we're going to be looking at 3.1 exponential functions, and highlighted will be the target that we're going to be focusing on in this video, which is being able to evaluate, analyze, and graph exponential functions. So our intro to the lesson is just talking about some real-world impacts. And so we're starting the lesson asking, what do you need to survive in this world? Now, we all know that we need math, but there's some other things too that would be probably just a little bit more important. So the first one that I'm sure would come to mind would be oxygen. And the interesting fact there is how long can we go and we can still survive. And when I did some research, I found out that that's approximately 3 minutes that we can go and survive without oxygen. The next one that I'm sure that would come to mind would be water. And water is about 3 days that we can go without water. Some people have been known to go over a week, but the rule of thumb for water is about 3 days. And food, we can go about 3 weeks. So what we're going to be focusing on is looking at water. Okay, so us being the Great Lakes state, we're very fortunate that we live in an area where there's plenty of fresh water. So let's see if you can pause the video and see if you can fill in the blanks with some words that you think would make sense. So, worldwide water consumption has increased rapidly over the last several decades. Most of the world's water is used for agriculture. The growing population has resulted in an increasing agricultural demand. The increase in water consumption can be modeled using, drum roll, exponential functions. Now, I'm going to say in defense, I read a recent farm article that said that actually in America, more water is used for lawns in the Great 48 than what's actually used to produce farm crops. So while we're concerned about agriculture, that's something that, when there are droughts, that there are regulations for people to not use water for lawns when that can grow back after the drought is finished. So as you probably recall from Algebra 2, exponential growth is going to look something like this. So as we look at water consumption, that has gone up for agricultural reasons, for population regions. That would be a model that when we clicked data and we plot enough data, we would find that a curve, a best fit, would be an exponential. So by coming up with a function, we're able to make predictions and use that data to predict what water consumption will be in the near future. So can this go on continually? No, we would expect that there's going to need a different model that will predict how the consumption will go. And so we might look at the data coming up and leveling off. And that's something that's called a logistic growth curve. And it's something that you discuss in a Calc 2 class. So on page 2, there's a big difference between an algebraic function and a transcendental function. We're used to, in a large part of Algebra 2, talking about algebraic functions. So these are known to be linears, quadratics, cubics, rationals, which we recently did, radical functions, and power functions. In contrast, transcendental functions, we're going to be dealing with exponentials and logarithmic. So these are two types of functions that we say can't be expressed in terms of algebraic operations like addition, subtraction, multiplication, and division. So we say that they transcend algebra. So an example of an expo could be 3 to the x power. An example of a logarithmic would be log base 3 of x. So we're going to be spending a lot of time in chapter 3 discussing transcendental functions. We have spent time going over the algebraic functions. So the definition of an exponential function, we're going to be looking at some key features. And when it comes to an exponential, as you know, there are growth. Let me fix that. So the two main type of expo functions are functions that grow, like our water consumption, and looking at things that decay. So we could look at carbon dating, where we look at the amount of carbon in a once living object and that amount decaying, or looking at nuclear waste and how that decays over time. So what's important to know is that when you are growing, your base is greater than 1. So looking at our forms for an exponential, the base of the exponent would be greater than 1 for growth. And when it comes to decay, our base has to be between 0 and 1. So base greater than 1, and with decay between 0 and 1. So we're looking at examples that we see right here in cases where our base is either greater than 1 or it's between 0 and 1. So when we look at the examples to the right here, we're looking at values where the base doesn't meet those criteria. So would not be an example of an exponential function. So a way to graph an exponential is to look at your inputs versus outputs. So I've made a chart just putting in some easy to determine values. So if I have an exponent of 2, I get 16. If I have an exponent of 1, I get 4. If I have an exponent of 0, I get 1. So again, looking at our exponents, as they drop down by 1, we can see that we're dividing by the base. So we're going to continue on. If I divide by the base, I get 1/4. And if I divide by the base, I get 1/16. So when we look at our values, we should be seeing a relationship between a positive exponent and a negative exponent. So there's our inputs and our outputs. So plotting our data, looking at the ordered pairs, we can see where we have a horizontal asymptote as we go to negative infinity, and the curve would go something like this. So that is a graph of a basic exponential growth where our base is 4, and anytime our base is bigger than 1, it's going to grow. So our domain would be all reals. Our range, looking at the outputs, are going to be greater than 0, and they're going to go to infinity. The intercepts, there are no x-intercepts. And our y-intercept, I will highlight right there. So when x is 0, our y-intercept is 1. So that's right there. Asymptotes, we have a horizontal asymptote. And that equation is y is equal to 0. And then our end behavior is going to be the limit of f of x. It's going to be only going to negative infinity, and we're going to get closer and closer to 0. And what we notice is that this function is strictly increasing. So what we learned in our prior unit is that if you have a function that strictly increases, I'm going to have an inverse that will strictly increase as well. So I'm just going to do a dashed line going across like so. And we could graph the inverse that would look something like this right here. So I'm going to note that. That's going to have implications as we study logs. So where is it increasing? We're going to put for all reals. Now looking at this one, we can see that our base is raised to a power, and let's just talk about that. One thing that we learned in Algebra 1 is that we can write this as 5 to the negative 1 to the exponent of x. So this would be a way of writing the function. And so what we learned about negative exponents is this can be written as 1 over 5 to the exponent of x. So this would be my function notation for the function b. So again, my base is between 0 and 1, which means we're going to have decay. So I've made a data table with an exponent of 2. I'm going to get 1/5 squared, which is 1/25. Plugging in a 1 is easy. I'm going to have a value of 1/5. 0 is easy as well. Anything to the 0 power is 1. And now when I put in a negative 1 exponent, let me do a little bit of work there. I get 1/5 to the negative 1. I'm going to be looking at, well, what was my value with a positive exponent of 1/5? And what I'm going to do is I'm just going to invert that. So I get 5 over 1. So doing the same thing here with an exponent of 2, there's a relationship between an exponent of 2 and an exponent of negative 2. So I'm just going to invert that as well, and I get a value of 25. So on our next page here, we have our basic blueprint for an exponential function, just comparing the two types. Again, when we have growth, base bigger than 1, and when we have decay, our base is between 0 and 1. Noticing that both have the same y-intercept because anything in the 0 power is 1, and going over some of the features that we just discussed on the function. Noticing that they are continuous, that they do pass our continuity test anywhere on the domain. Now we're going to do some transformations of exponential functions. So what I want to do first is just talk to you about transformations that we did with quadratics. So a basic quadratic is just an x squared function. So when we put into the function an x plus 1, we knew that this function was going to slide to the left 1 unit. When we had a negative in front of the quadratic, that meant that we were going to have a flip. So some of these same properties, when we look at an exponential with the exponent being the place of the input, we're going to see some of these same transformations that take place. So looking at our 3 examples, we notice that each function has a base of 1/2. So what we're going to be doing is looking at the transformations. So for graph A, I've done a data table of x and y values, and I plotted the inputs and outputs as ordered pairs, and I can see that a graph is sliding to the left 1. So where I used to have a y-intercept at 1, I now have that left 1 unit. So that would be a complete graph. Let's just put in the horizontal asymptote right there of the first graph. Looking at the second graph, we can write it as a base of 1/2 to a -1 power times x. So remember that when you have a -1 power, we're going to flip the fraction. So that becomes y is equal to the x power. So I find that that's easier to graph than dealing with the 1/2 to a -1 power. So what we're going to do is we're going to plot data values and then just construct our graph. So looking at some inputs of 0, 1, 2, and -1, we can see our trend for our graph to increase. So while it looked like we would have an exponential decay, it actually ends up being exponential growth because our exponent has a negative value. So looking at our third graph, we see that the base is between 0 and 1, so that means we're going to have decay. And we would look at the leading term, it's negative, so that means that we're going to have a flip. So looking at our inputs and looking at our outputs, we can plot our data values. So what you see on the graph are those points plotted. I did include that if we put in a 2, we have 1/2 squared, which would be 1/4, times a -2 would give me the -1/2. So plotting our inputs and outputs, we get a curve that's approaching the x-axis as we go to positive infinity. So again, looking at our values for exponential decay, our base needs to be between 0 and 1. And for growth, our base has to be greater than 1. So when we look at values between 0 and 1, the closer the b value is to 0, the faster the decay will be. And the closer, or the further rather, let's switch that to the further the b value is from 1, so the bigger that base gets, the faster the growth will be.